Welcome everyone, and thank you for joining this webinar. Today's presentation is about a new offering of linear actuator products from Applied Motion. My name is Eric Rice, and I'll be your moderator for the next 30 minutes or so. A quick note about this webinar series. This webinar is a part of a series that started back in April, and we've done one new webinar presentation roughly every 2 weeks. After today's presentation, we're going to take a break to regroup and plan for future webinars, so please be sure to keep your eyes open for new topics in the coming months. All of the webinars presented so far have been recorded, and the recordings have been made available for watching on demand. You can find those recordings on our website. There are links on the homepage and in the news section, and you can also find them on our YouTube channel. Regarding questions for today's presentation, there will be time at the end of the presentation to answer as many questions as we can fit in. Please submit your questions using the webinar control panel. And any questions we don't get to during the Q&A session will be followed up via email afterwards. So without further ado, let me introduce today's presenter. Leo Liu graduated from the University of Melbourne, Australia with a degree in electronics and received his Master's of Business Administration in 2013 from Monash University, also in Melbourne. Leo joined Moons Industries in that same year. He gained experience in R&D, engineering, product management, and marketing. He moved to the United States in 2015 when he joined Applied Motion Products. And here he has focused his attention on key business areas such as marketing, sales, and engineering. Currently, Leo serves a dual role within Applied Motion. He leads the application engineering team in assisting our customers and channel partners, and he contributes to the product management group in launching new products. And with that, I will turn everything over to Leo for the presentation. Leo, it is all yours.
Thank you, Eric, and hello, everyone. Welcome to my linear webinar today. I assume most of you guys are relatively familiar with Applied Motion products by now. Applied Motion products is specializing in designing drives and motor systems for both steppers and servos, and also including brushless DC type of motors. In recent years, we introduced the concept of integrated motors, which combines the motor, encoder, and drive into one single package. And more recently, we introduced the StepSERVO product line, which is a closed loop type of control and results in greater system performance. With the increase of system complexity and more expensive labor cost, and the new trend for the motion control market is go compact, easier setup, and more production friendly. And this is why we bring us to the topic today. Integrating a already integrated motors with linear screws and linear actuator to make that ultimate all-in-one package. So there are several different ways of product forms that Applied Motion is presenting today. Integrated motors with linear screws includes a drive, encoder, motor, screw and nuts, and also we have a separate system where the drive is separate from the motor package. And on top of that, we also have a linear actuator type, which includes additional features such as object carriages, linear guides, supporting bearings, and some other installation features. Depending on your application, each of these products was suited differently. So in a traditional way, when you try to motorize a object, there might be a couple of things you need to think about before you start doing that. What I'm going to automate, and how am I going to attach to my object, and how fast I want to go, and how long I have to be going with, and what kind of motion do I need to use for control these axes, and how am I going to move that. Typically involves a motor, a drive, and often depends on the motor type, the accuracy, and the capability of the motor. Once you figure out all the motion parts, then you have to think about the fixtures, the linear screws, and how to put them together as a package. And that often involves mounting patterns, shaft couplings, so on and so forth. Once you have all those figured out, then you have to run your system and test them, see if that actually works. And finally, you need to think about how can I replicate the system quickly and turn that into a production process. During this process, you might also have other considerations, such as cabinet space, cable management, size of the motor, size of the screw, figure out how you're going to put them together, if there's any bearing support I need, motor drive configurations, and even encoder calibrations. And the list just goes on and on. So this is our solution. As you can see from the pictures, the unit involves less parts. All the parts on the previous slides are kind of put into the one single package. Compared to the conventional type of solution, all the critical motion components are there, the driver is there, the motor is there, encoder, screws, and nuts, and so on. However, all the linkage components, such as the mounting plates, the couplers, the cables between the drives and motors, are kind of gone. Similar situation goes to the actuators, the carriages, and the supporting features are all built into that small actuator right there. And more importantly, that actually changes your purchasing, the way of your purchasing. You have less items to consider. If you talk to us, what we do is we will, based on your motion profile and the loader requirement, you will see a push force curve from us. It looks like the one on the right-hand side. Then we pick the motor and screw combination for you based on your requirement, and then that's pretty much ready to go. So before we dive into all the details about linear motions, I just want to touch base on StepSERVO technology. Jeff Kodik, our CTO, did a great presentation a couple weeks ago about this technology. I won't go into too much detail of that, but overall, StepSERVO is going to boost your performance on your linear applications because its capability. So first of all, it is more power. You will get 25% more torque out of the similar motor package, and peak torque is also available. And secondly, the control resolution from the StepSERVO motor is 20,000 counts per rev, which means if you have a 2mm leads with this amount of control resolution, your command position can be as small as 0.0001 millimeters in a good saturation. Also, servo-like control experience will allow you to not accumulating position errors during the running of during the operation of the system, and also it has become less load dependent on your axis. High-speed operation also become available because the traditional stepper motors, they run from 5 to 15 RPS, whereas StepSERVOs, they go as high as 50 RPS. Apart from the performance, it is better life for your motion axis, actually. So the great thing about StepSERVO, again, it's closed loop control. So it results a more efficient system. Less current goes into the motor, means less heating from the motor, and in turn, you can run the motor longer with higher duty cycle. And less current in the motor also means less noise and vibration during the phase changing of the stepper motor. Imagine you already have a ball screw on the system. The screw is making so much high-pitched noise. Adding the stepper motor noise, it's not very pleasant to hear. Less vibration also means less damage to the screw and the bearings, so that will increase the lifespan of your actuator. And finally, less power consumption is always very welcomed by any type of battery powered system, for example, an AGV car. And finally, StepSERVO motors with the closed loop, they don't really store out because the encoder will always try to bring the motor back to the position. And also, StepSERVO motors have other features like hot stop homing, where sensors can be eliminated from your actuator. And more recently, we introduced the true counter absolute encoder motors, and specifically designed for this type of purpose. Product selection-wise, you guys probably already know we have a wide variety of products for the linear applications, NEMA size 11 all the way up to size 24. And we have various of control options from I/O control all the way up to field bus and internal programming. So back to the topic of linear. When you select a linear system, one of the most common questions I get asked is, do I need a ball screw or do I need a Leadscrew system, and why? A lot of the assumptions were made by people that ball screws are more expensive, they are stiffer, they provide higher accuracy, so they are actually better for me. But in some cases, it's very application dependent, and we will go through some of those. In general terms, the basic difference between Leadscrew and the ball screw is that the ball screw uses ball bearings to eliminate the frictions between the nuts and screws, whereas the Leadscrew, they don't have that. The rolling nature of the ball screw eliminates the sliding friction associated with the Leadscrew, which brings you smooth motion and a more efficient system. And looking at the graph, you can see ball screw is over 90% of efficiency, where the Leadscrew system roughly around 30% to 70%, depends on your product choice. With the low friction of the ball screw, it allows the ball screw system to go higher on the speed, higher duty cycle for your applications. As you can see, 15 RPS for a typical Leadscrew, ball screw 50 RPS. Since the stiff nature of the ball screws, so they do offer higher accuracy and a higher repeatability, and also it allows them to run for a longer lifespan. However, because the ball screw are metal to metal contact, so in general cases, the noise level is pretty high. So when you're working in an environment where noise is not welcome, Leadscrew is actually the better selection there. Cost-wise, Leadscrew systems are a lot cheaper than ball screw. Therefore, if you have a system where the actuators can be easily replaced, maybe Leadscrew is also the option to go there. And finally, Leadscrew offers a self-locking function, which is not available from the ball screw, and it is very beneficial for any axis that's vertical or where a holding force that is needed. Okay, so what is the difference between repeatability and accuracy? In a linear system, accuracy meaning the degree which the final position matches the command position, whereas the repeatability meaning the ability to return to the same position multiple times under the identical conditions. A system can be accurate but not very repeatable, and also can be pretty repeatable but not very accurate. And I use the example on the right-hand side where a system is trying to achieve the position of 300 millimeters with a plus and minus 2 millimeters. And in a consistent system, maybe the actuator will always hit a 302 millimeter position. So it is repeatable, but at the same time, it is not very accurate. In other cases, an accurate system can always hit between 300.5 to 299.5, so on and so forth. But so it is very accurate, but at the same time, the repeatability is not as great. So how can I make it better? So accuracy, that can be improved by having an optimized drive and motor combination. Remember a couple of slides ago, we talked about step servos, with the high control commandable position. That would definitely help on the accuracy. But on the other hand, for the repeatability, it has more to do with your mechanical setups. If you have a backlash nut or if you're using a ball screw, it will already help a lot. Other factors to consider is actually temperature change, the material of the screws, if there's any expansion or contraction going on during the operation. So how much force do I need for my design? That really determines your product choice for your system. So the maximum speed of the linear motion is determined by the maximum rotary speed that's allowed from the motor times the lead of your screw. For example, if you use a 2 millimeter leads and the motor can run as high as 10 reps per second, your linear speed is going to be 20 millimeters per second. Then you will look at the maximum allowable force from the motor and the screw combination. Using the graph example I have on the chart, it is a TSM 11 step servo motors with a 2 millimeter leads and 6 millimeter diameter bar screw operating on the 24 volts power supply condition. And as you can see, there are actually two datas on the curve. One of them is the maximum push force allowed. So for TSM 11 with this type of leads, you get up to 180 Newton of pushing force at a speed around 20 millimeters per second. And the purple line indicates the mechanical limit. Because the motor is such a small motor with a very skinny shaft, so you don't want to go actually over 100 newtons of push force. Anything over that might lead to damage on your system. So overall, I would recommend a push force around 140 newtons for this motor and screw combination. So what happens if I want a motor with more power? So you can change to a bigger size motor with a bigger size shaft. And on the other hand, what happens if I want to go faster? You can pick a larger lead size, but just keep in mind, larger lead size will meaning half of the push force. Leadscrew has this nature of self-locking function. It is from the nature of less efficiency and the larger friction from the lead screws. When the coefficient of friction is greater than the tangent of the lead angle, the lead screw will lock itself. This is a great feature for any axis where holding position is needed. It eliminates the need of a brake, an external brake, or any type of holding device to sustain the load while they're in position. For a ball screw system, you might need to use a brake, and that also means you need extra components, you need to do additional wirings, and there will be certain control mechanism for this purpose. With that all said, not every single lead screw will have the self-locking function. For applied motion screws, if you pick a screw that's less or equal to 1/3 of the screw diameter, the self-locking function will exist. For example, if you have a 2 millimeter lead with 6 millimeter diameter screw, there will be self-locking function. And the force of the locking can be calculated based on that formula shown on the chart. So a TSM 11 with 120 Newton meter of holding torque, you will get roughly around 628 Newton lock force. And it is great for any type of setup axis or vertical axis. Product offering wise, Applied Motion have both ball screw and the lead screw options, integrated units and separate systems, step servos. And we offer leads from 1 millimeter to 20 millimeter in pitch, up to 500 millimeters in travel length, 300 Newton push force, and other options like nut size, different nut shapes, supporting varying features are also available. What happens if you need an open loop stepper motor? We also have that. Feel free to contact us and we can talk about it. So now I'm going to talk about some of the application examples by using either a ball screw or lead screw system. So in this case, the customer has tried to design a position table for a CNC type of machine. This involves 4 to 8 axes per table for this particular application with multiple positioning control that's required. So for the customer, they actually need 120 newtons of push force, and they only want to run at a higher speed at 10 millimeters per second. Once that's in place, once the position is in place, the top of the manufacturer, or let's say the CNC cutting, will be working, whereas the axis was just holding the load. So it is a very low speed movement, and the duty cycle is not very high, and they do actually require that self-locking function. So lead screw was our choice. And I actually picked the 1 millimeter pitch for them, so that it allows a holding force up to 1,000 Newton meters, which is great for the system. In addition, the TSM11 uses RS-485 for positional commands, and it can actually change position on the fly. And also they can daisy chain all 8 of those axes together, which is great for the application. And the factor grippers or laser cutting heads, they also kind of gets a lot of benefit by using integrated units. But in this case, ball screw will be the product choice. In a typical application like this, the movements are very frequent, and it's very small movements. And also the speed can be pretty high, depends how fast the customer want to move it. And also during the operation, it's very unlikely they will shut down the axes, and the holding position is not very much needed. Low motor heating is one of the requirements, because the system can get heated pretty quickly if you are using an open loop stepper motor. So StepSERVO motor was kind of their choice there. And on the other point, because of the low vibration nature and the wider range of speed for the laser cutters, it actually makes a higher cutting quality for the customer. Safety feature wise, there's involves travel limits, and sometimes even a safety sensor, and they actually just directly mount them towards the backside of the motor, and that really helps on the wiring for the customer. 3D printers, it's a linear application. It is definitely a fast-growing industry in the past 10 years. It started with a traditional XYZ gantry kind of system with all the lead screws. They are cost-effective. Normally, they will use a higher lead for the high-speed requirements. And I would say the accuracy is within their acceptable range. However, as the industry moving forward, the product offering become more specialized towards certain customer needs. For example, a consumer type of product, they still want to have a compactness, and they actually focus more on the quietness of the system, and the accuracy not so much. So Leadscrew is still the optimal choice for them. But on the other hand, all the commercial, industrial focused printers, they want a higher speed for the prototyping, and they want a high precision quality for the printing. So in that case, some of the customers started choosing ball screws for the XY axis, while still using the vertical axis with a lead screw, because it is lower duty cycle and the holding purpose is well utilized. Automated setup axis is one of the bigger topics for any factory automation industries right now. Historically, when the production cycle ends, some factory workers have to come into the factory, and they need to set up each of those axes accordingly with the new production requirements. It's very time consuming, and it is a tedious process. In some cases, customers even say, the setup time is even longer than the actual production time. So a Leadscrew with a TXM24 integrated package is an optimal solution for them. It has the internal programmability, it has field bus control if they needed to use, and since it's an integrated unit, it's completely out of their main, what they call production tooling cabinets. And the speed is relatively low, and the frequency of the travel is not very often. So Leadscrew is perfect for them. Plus, they will use the self-locking function to hold in place. So recently, we also introduced the true counter absolute encoder. So homing become an unnecessary process for some of the customers, and that's a very welcomed feature by these industries. And also, just keep in mind, a closed loop StepSERVO system, even when you just leave them on during the production, it still doesn't really consume a lot of current, because to keep the control units going, it only requires less than 0.1 amps. So smart actuators. So the smart actuator is where we combine the screw of the motor and add on additional features such as the carriage, the linear bearings guides, and other installation features. For applied motion products, our focus is going to be on the miniature size of the actuators, and because that's where compact become very critical. And our main product line will go as small as NEMA size 8 all the way up to NEMA size 17, and we have that both available on StepSERVO and stepper motors. And typical pitch size 1 millimeter up to 12 millimeter in pitch, and the stroke length up to 250 millimeters total. Our design philosophy for these smart type of actuators is compact and also convenient. At the first, we try to minimize all the linkage and the supporting components by removing the couplers and design in the bearing support features, integrating the carriage with the nut, and in turn to maximizing the usable stroke length it's available to you. As you can see from the drawing, the total length of the actuator is the motor length plus only 58 millimeters for the carriages, and the rest of them are all available travel strokes. Secondly, we try to minimize the side spacing going around the actuator. That's why if you look at this drawing, the motor and actuator looks almost in line, like a tube, because it requires less side spacing from your system. In order to provide more convenience, we're designing all those installation features. We have threaded holes for base plate mounting, travel sensors, and we have multiple directions for the carriage mountings on it. So the point to consider when you're building an actuator system is rather similar to when you choose a screw. On the side, you can see that's a demo unit I built for my own self-education purpose, or let's say demonstration purpose as well. During this process, I will first pick up, based on the duty cycle, I pick up if I need a ball screw or lead screw. And then based on force and speed and length requirement, it all goes into that product selection process. On the other hand, there's other factors I have to consider. If you look at the y-axis, it involves a large hanging weight on the side of the actuators. So I actually put a supporting guide rail on the other side to counterbalancing the weight load. Whereas the z-axis, it's not too much of a hanging force. It's pretty close to the actuators, so I utilize the side mounting features and the top mounting features all together to put to mount the NEMA size 8 actuators. From the wiring purpose, the miniature NEMA size 8 motor is an open loop stepper, so I put the sensors directly onto the actuators, whereas the two smart actuators, I use the hard stop homing function, and they're using encoder positioning for the control, so there's no sensor needed for those two axes. When you're designing an actuator in your system, the direction of the load and the mounting of the load plays a critical role in terms of product selection. One of the big reasons is the moment of torque. Depending on your system direction, the torque can be completely different. Let's use the example on the right-hand side. When the object is hanging out of an arm on the side of the actuators, and when the actuators start to moving, there's at least 3 types of moments that's associated with this motion. The moment of tilting, and the moment of great gravitational force, and also what I call the rotation of the arm is also a moment. So the goal is to design a system where compare the ratio of each of the potential moment torque to the maximum allowable torque force, add them up, they have to be less than 1. Then your system most likely is fine. So what happens is I think there's a couple of ways you can either counterbalance the weight, or you can providing a support on the other end of your object to counterbalance the moment. As you can see, if I put a guide rail right underneath that blue box there, it will take care of the tooting. I will take care of the gravitational force and also the rotational moments. Couple of examples on the applications. The mini actuators are great for the system where space is limited, but an engineer don't really want to work too much, onto designing a screw system. They want to make it easy and ready to go. So we have multiple applications in the inspection or vision systems. One of the application example I put it here is for the phone and tablet touchpad testing for both design and production process. The actuator moves to different side of the touchpad and touching on multiple positions and try to see if they actually perform the same. One of the great advantage you get from the StepSERVO motor is actually the torque control capability. Because with the newer generation of touchpad, all the phones and tablets allowing a pressure sensor control. So with that in design, the TSM11 will push down with a certain amount of torque force and with a certain amount of holding time to testing exactly that function. In other business cases where a customer have a bigger system, it involves a lot of moving parts. So we actually help them to select if a screw motor or actuator is more suitable for that particular axis. Let's use semiconductor equipment as an example. In inspection machine, it normally involves camera movements, alignments, focus, and product insertions, and so on and so forth. So for the base plate, TSM23 with the ball screw, it's great because the weight is heavy on the top, and they can design their own guides on both sides of the plate to make it evenly supported. And for the y-axis selections, TSM17 was a choice because it's marginally reduced in the load weight and also the size of the load. Z-axis, they like the NEMA size 8 because it's very small, the camera is light, and also it's a very minimal space requirement. And NEMA size 11 motor actually is perfect for wafer carrying. Again, because wafers are pretty light on weight and the space is really tight. For all these axes, they all talking more about RTU, they all can be daisy chained, they all working on the same DC bus voltage. And that was one of the great choice for our customer. Similarly, it goes to a multi-axis life science or lab automation. The loader in general are not very heavy and they need high position accuracy controls. Operation spaces are very tight. Clean room kind of environment is always needed for the handlings. So we design our system with a combination of rotational motions and linear motions. So how do you approach us? With the combination of an integrated motor and a linear stage, the variation of products can be huge. And I think the best way to approach Applied Motion on these products is talking to our regional sales manager, talking to our application engineers. We will define the motion solution together. We do the product selection together. Then we prepare a drawing for you. We talk about the commercial decisions, and finally we deliver the prototyping products based on the choice. And then everything passed your test, we are ready to go into the production cycle. And this is the end of my topic, and thank you guys. Now I hand it back to Eric.
Thanks, Leo. Great job. We've got a little bit of time for questions, so let's dive right in. A number have come in so far, so let's see how many we can answer here. As a reminder to everyone, if you'd like to submit a question, simply type your question into the webinar control panel. So we'll start off here with a question from Steve. He asks, is there any way to gather information about torque that the motor is putting out? For example, Leo, in a servo system, we can monitor current to check the health of the mechanical system. can we do something similar with step motors?
With our StepSERVO, it can totally do that because StepSERVO, the current is very nicely regulated. So you can easily monitor the current and seeing how much it is pumping out from the drive side. So it is totally capable from the StepSERVO motors that we were just talking about.
Perfect. Okay, we got another question from Mike. He says, it looks like you guys have hollow shaft motors and integrated motors. Can I use my own screw?
I would say yes to this question because, and it also depends on what kind of installation methods you want to use from the screw. And that's definitely something we can work with, and we just need to discuss all the details about the mountings and installations. So I would say yes.
Cool. Okay, so we got a question from Martin. Sounds like he's a little bit familiar with the product line. He says, I know the MLAs are currently application-specific designs, but have you established any max payload or max travel constraints for each of the sizes? So first, maybe, Leo, you could talk about what are the MLAs for other people that don't know what they are.
Okay. Let me go back a couple of slides. So this, the ones with the black motors, they are the MLA type of actuators. And Martin, back to your questions, if you have a product selected already, I can definitely work on the details and show you all the ratings and everything. No problem on that.
Yeah, I think one of the things we've talked about is, as you mentioned just a minute ago, Leo, because of the broad selection of options that we have, we aren't putting together like a standard catalog yet. Eventually we may get there, but right now it's more about, what are your specific requirements and how can we best meet those?
Yeah, exactly. Because the product selection is so wide and, we have 3 or 4 types of screws and nuts. So each one of them can work slightly differently. So yeah.
Yeah. We got a question here from Norman. He says, is there an option for linear encoders to minimize mechanical backlash of the linear actuator?
So linear encoders, with our separate system, the SSDC, you can actually input a linear encoder signal into the drive. And then for the position control, the SSDC drive, we're actually using the linear encoder for your position feedback. As a solution. So yeah.
Okay, cool. I didn't know that. A question from Jeff. Do you have any solutions for IP65?
IP65 currently, we don't have that on the screw side, but definitely something we can work on. And if you have an application specific, we can look into that for you. No problem.
Cool. And because we do have it on the motor and drive side, the integrated motor side.
Right.
Yeah.
So we have that,
but not on the actuator.
Yeah.
Okay. I think we've got. I want to be respectful of time. We're a little bit late, or a little over time, I should say. We got a question here from Dave. Are you willing to supply the actuator only without the motor?
Yeah, I think that we need to talk offline, specifically, because the concept here is, not having the couplers and things like that. But yeah, definitely we can talk about that. No problem.
Right. Yeah, good point. Because these are very closely coupled. The shaft, there is no coupling between the shaft and of the motor and the screw.
Yeah, the screw goes
Makes
straight.
Perfect sense.
Yeah.
Awesome, Leo. Great. Thank you for answering those questions. As a reminder to everyone, if your question did not get answered, we will be following up with you via email. We want to be respectful of time. Also, before everyone starts signing off, there will be a follow-up email after the webinar with a short survey. Please take a minute to complete it. It will only take you a minute, and we really do appreciate your feedback. So with that, thank you again to everyone for attending. We greatly appreciate your interest in Applied Motion Products. Have an excellent rest of your day.
Thank you. Thank you, guys.